Hey guys, my name is Matthew. Today I'm going to be introducing Quicksort. Sorting is one of the most common problems in computing. The way in which we do a sort has a strong impact on its efficiency. Because of this, Quicksort, being one of the most efficient sorts, is widely used in industry. Furthermore, within this, the way in which we perform the Quicksort using the partition function, which we will explore later on, has a strong impact on the efficiency of the partition function. Let's now examine the partition function, which is one of the two crucial elements out of the partition function and the Quicksort function. Within the partition function, we have an array and we have a partition P, which is returned by the function. We want to ensure the property that everything above the partition index we see here is greater than the value in this point. And we want to ensure that everything below the partition index is less than this value. By repetitively using smaller and smaller sections of the array, we eventually ensure that the array is sorted. Let us now examine the partition function. In the partition function, we want to ensure a certain property. This property is that everything below the chosen partition, say it was equal to this index, everything below this must be less than the value in the partition. And everything above this value, above this index, must be greater in value than this value. So today we are going to be talking about the method of partitioning, of choosing the pivot as the last element in the array. So a pivot is the value we choose to be the value we swap into our new partition index once we finish the partition function. Let us examine how we run this particular example where we choose the pivot from the final index of the array. So in this particular example, we have the array 9, -1, 2, 4, and 3. Notice that it is an array section, not necessarily the entire array, and we have the values high and low for this array. These remain constant throughout this particular function. We select 3 as the final element as our pivot. We then set I and j, which are two indexes we will close the range between, and when we eventually pull these together, we will have found our partition index. Let us work through how this works in this practical example. So we start off and notice the value in j. 4 satisfies the property that everything above the partition is greater than the value in the pivot. So since 4 is greater than 3, we do nothing and we decrement j. We now examine the value in j now, which is 2. This fails the property since 2 is less than 3. We wanted it to be such that 2 was greater than 3, but obviously this is not true. So we stop decrementing j. We now examine the value in I. Since 9 is not less than 3, we stop incrementing I. If 9 was less than 3, we would increment I and continue the process. Now that we have fixed the values of I and j, we now swap these values since I is not equal to j. So let's do this now. In C, this will be performed using a simple swap function. We now perform the process we described before once again, and we will continue to do so until j is equal to I. We decrement j, and notice that once again, -1 is not greater than 3. Therefore, we stop decrementing j. We now examine we now increment I. The entire process now stops since I is equal to j. Since this process has stopped, we have determined one of two possibilities. Either the value in the now value of j, or I, is the new partition index, or the value one above this is the new partition index. Which one of these is the partition index depends on how we would satisfy the partition property. We want to ensure that once we swap our pivot 3 with one of these values, then everything below 3 would be less than 3 and everything above 3 would be greater than 3. So let us consider swapping -1 and 3. -1, if it was placed in the final element, would therefore cause the array to be out of order. So therefore, we must place 3 in the location of 9. These are now swapped. Now that we have made our swap, we return the new partition index. Since we are in C, we are using zero-based indexing. So we have the index 0, 1, and 2. So therefore, we return from our function the value 2. So let us now briefly discuss the quicksort function before resuming our discussion of the partition function. So now that we have received our partition index, which is 2, from the partition function, we now use this to divide up the array and reapply the quicksort function on those sections of the array. So here we have the upper section of the array, and we will reapply quicksort on this section. And we also have this section of the array, and we will reapply quicksort on that section down here. Within this also means that we will reapply the partition function. As discussed before, we will work with smaller and smaller sections of arrays, and therefore this process will eventually end and we will have a sorted array. So let us now examine the upper section of the array and how the quicksort function works on it from now. So we now have the elements 4 and 9. These are in order. We will have the pivot 9, and since 4 is less than this value, no swaps are made. Let us now examine the lower section of the array. We now have the values 2 and -1. The pivot is -1. So we then examine the value in 2. This will ensure that I and j, since there is only one value, will be equal to each other initially, and therefore the process which we had a loop in before will never actually begin. We will then notice that -1 and 2 will need to be swapped. So we will do so in this scenario. Thus, for those smaller sections, we have completed the partition function. In this particular partition function, we will have returned the value 1, since we left the pivot as it was, the value 9. And in this one, since -1 was originally the pivot, we will return the value 1, since the new partition, we will return the value 0, since the new partition is the value 0. And the value returned from this one is 1. We then further reapply the quicksort function. Since 2 is the remaining section of the array, we will look at the value 2 inside its own array, since it has only one value, then no swaps are performed and no resorting occurs. Behind the scenes, we will then look at everything below the partition, which is an empty array. But obviously nothing happens in here since there are no values in the empty array. Similarly, the value 4 is the remaining section of the array before the 9, and therefore we examine the 4 in its own separate array. Since there is only one value, once again, we do not perform any sorting. Similarly, everything above 9 is the other section of the array, but since it is empty, nothing actually occurs. Therefore, we now have the following values in our array. -1, 2, 3, 4, and 9. Clearly, this is sorted, and we have performed the entire quicksort function on our example. Let us now look at an example in real time using code. So hi again guys, so right now we're going to examine how Quicksort works with some implemented code. So this particular code uses the example I showed you on the board, which is the array 9, -1, 2, 4, and 3. And within it we have two main functions, a Quicksort function, which as described before, uses the partition function to get a partition index and then use this to divvy up the list. The partition function within this then loops decrementing and closing the range between I and j, and swapping whenever we find elements which are out of order, and failing the condition, which we recall is that everything above our chosen partition at the end of the function will be greater than that value in the partition, and everything below this value will be less than this value. Also notice that we have a swap function to swap two elements. This is quite simple using a temporary variable. So let's check whether this code works. It might be a little embarrassing if it didn't work. So we use the DCC command as you will have seen in class. So it compiles. So as you can see, we had the original array as we set out, and we now have the sorted array as we desired. Now, the purpose partly of showing this code is so that we can print out the values stage by stage. Let's do this. I wrote some code to print out a particular section of the array, section by section. So let's recompile and run it again. So as described on the board, we initially used the partition function to attain the array 2, -1, 3, 4, and 9. And as we can see, since our partition index was index 2, which had the 3 placed into it after the initial application of the partition function, we then work on the array 2 and -1. Since Quicksort is a recursive function, which means that it applies on itself, as we can see in this code, it dives in at the deepest level possible. So before we work on the second half of the array, we dive down to the very smallest section of the first half of the array. So we then work on the left-hand side of the -1 and 2 section of the array, which we receive after this particular running of the Quicksort function. And since everything before the -1 is an empty array, we work on an empty array within the Quicksort function, which obviously does nothing. Similarly, with the section above the -1, we work with a 2, which similarly does nothing. We then work on the second half of the array, which, as we recall, contains the 4 and 9, and the partition is set to 9, and the part before this is the for, so the quicksort and partition function perform nothing on this section of the array, as it is only one element, and everything above the 9, because we are using the 9, returning the index 1 to divvy up the list, everything above this is an empty array, so therefore nothing happens similarly. So now that we have examined how the quicksort function works, how it applies itself and in which order it runs, let us now look at some code we have which prints the values. Actually, before that, let's just look at what values we had in the quicksort after the partition. As we can see, these values show everything I just described. So it shows the partition index at each stage, as we described in the lightboard example. Let us now print out what values we have in each application of the partition array. So this will print out the entire array section within the partition function. Okay, so notice that in the partition function, we initially had the array 9, -1, 2, 4, and 3, and in the next section of the loop, we had swapped the 2 and the 9, as these were out of order, as we discussed on the lightboard. This was because we decremented j and didn't increment I, as we had found that 2 was less than 3 and 9 was greater than 3. So these failed the eventual partition condition. Then recall that we closed I and j to index 1, but found that -1 is less than 3, therefore the 3 had to swap with the 9. Let's continue on to the next iteration of the quicksort. So then notice that the partition index was 0 because we swapped the 2 and -1, as we see here. And therefore the next iteration of quicksort worked on the empty array before -1, and then we worked on the one element array containing 2 after this. Then notice we worked on the second half of the original array, because we had gone to the very deepest level, to the very smallest elements, the smallest subsections of the first half of the original array, so we now work on the second half. So this contains the elements 4 and 9 after our original application of the partition function. So then we found that, and keeping in mind that these partition indexes here are for the entire array, so here we had the partition index was the very final element, which is index 4, which is actually the fifth element inside your array. And we then worked on the one element array before this in that subsection, which contained the elements 4 and 9, and then we worked on the empty array section after the 9. So, as we discussed before, we continuously divide up the array into smaller sections, fulfilling the partition property that everything before the partition is less than the partition and everything above is greater. And by working on smaller and smaller sections, we eventually have a sorted array.
Let's talk about one less detailed thing. The way in which we perform quicksort, as mentioned before, has a major impact on its efficiency. There are worst cases, and although these are quite unlikely, thus why industry is safe to use these quicksort functions, the appearance of these unlikely scenarios can drastically reduce the performance of a quicksort function. So in the worst case, our quicksort algorithm will apply itself in a relationship with the length of itself squared. So say that we had 1 billion elements. This could mean perhaps we had around 1,000 quadrillion operations being performed, which would take prohibitively long. Consider in comparison that if we have a very efficient quicksort algorithm, the scenario in which this would be performed would be if we always divide the array by 2 each time we find a partition. In this scenario, we might have a relationship in proportion to the length times the logarithm of the length. So this could, in comparison, only take about 30 billion operations, which is obviously much, much, much smaller. This could actually be performed by a computer and actually be sorted with 1 billion elements in an array. So this is actually achievable. Let's do a quick summary of quicksort. So the quicksort function is a recursive function. It continuously reapplies itself onto itself. It uses the partition function to find an index, which then divvies up the array for further applications of the quicksort function. This partition function ensures that we have the property where everything above the partition index we return is greater than this value and everything below the partition index is less than this value. By reapplying it continuously on smaller and smaller sections of the array, we eventually ensure that we have a sorted array. This concludes the video on quicksort. I hope you have a good time with your studies and have a nice day.